There. So we have another video about solution formation, and we'll talk a little bit about some of the energy transfer when it comes to actually making a solution out of a solute. So first things first, um, we've talked about it before, but when it comes to solubility, there's a couple of different things that affect solubility and how well things dissolve. But the cardinal rule is always like dissolves like. And I know we've talked about this many times. But polar solvents are always used to dissolve something polar or ionic, and nonpolar solvents are often used to dissolve something that's nonpolar. So benzene is a very common nonpolar solvent. So is hexanes that we can use in the lab. So just kind of keep that in mind. Water is almost always, it's the universal solvent. So unless somebody says something different, you can normally assume that is water. But there are steps to the solution actually forming. The first thing that needs to happen is we have to expand the solute. In other words, we have to separate whatever we're putting into the solvent into its components. So this could be something really, really endothermic. For instance, it could be separating an ionic compound, and if that's the case, step one here is breaking the lattice. So this could easily just be given to us in terms of here's the lattice energy for this compound. Okay, this could also be something a little less endothermic, and it could be maybe separating wax molecules from each other. And while they're nonpolar, they will stick together a little bit just because of the size, but for the most part, they don't have a lot of intermolecular forces. So the first step is always endothermic, but it depends on what it is that you're dissolving. Step two happens no matter what is going on. You have to separate the solvent, and most of the time this is water. So what I meant by it's always got to happen is that's the one thing that's going to be common no matter what solution you're making. So if I'm putting table salt into water and trying to make a solution out of it, as opposed to putting maybe copper chloride into water and making a solution, step two is going to be the same for both of them. Okay, they are endothermic. Step two is also endothermic because I have to expand the water from its other little water friends, and they're polar and they're attracted to each other. So to pull those apart is an endothermic process. Now, solubility and whether we actually make a solution out of our solute and solvent is all dependent on step three, because step one is endothermic, step two is endothermic. Step three is about the interactions of the solute and solvent. If that's a positive interaction, if we have something polar and we're dissolving it in something polar, then their interactions are going to be very good. And that means step three is exothermic. So when I'm putting table salt in water, table salt is ionic and water is polar, so their interactions are probably going to be pretty good. Now, if step three does not have good interactions, in other words, if step three is endothermic, then I can't make a solution. Okay, so if you think about the example of oil and water. So if I put oil in water, I have to separate oil from all its little oil friends, and then I have to separate water from all its little water friends, and then they have to interact. And I know you can think to yourself right now, they're not going to interact very well because water is polar and oil is not. So I'm going to have an endothermic process on all three steps here, which means as long as I'm stirring and as long as I'm shaking or as long as I'm inputting energy, I can overcome endothermic step one, endothermic step two, and endothermic step three. But the second I stop doing any of that, the solution separates because there is no longer any energy to make them interact. So again, expanding the solute, endothermic, I'm separating it into its particles. Water, most of the time anyway, we're separating that. And then third is our interaction. If this is exothermic, if this is a positive interaction, then I'm going to have a solution. If I want to know the energy of all of those solutions, I'm going to take step one expanding the solute, which again can be our lattice energy. Step 2 is the expansion of the solvent. And then step 3, and just add those all together, and we can get the energy that it takes to actually make a solution. So the solution overall could be exothermic or endothermic. It all is dependent on that third step. So in this example right here, we have an endothermic portion right here for steps 1 and 2, which I said would always be endothermic, but the step 3 is very positive, it's very exothermic, which means the overall solution is going to be exothermic. Over here, this is the opposite example. We have step 1 and 2, which is endothermic, and I get a little bit of exothermic step 3, so they interact a little bit, but not a lot. And that also leaves us with a then overall positive energy that we have to put into the solution to make it happen. So my first example would be the oil that we talked about, right? So if step 1 is endothermic, because I have to separate the water. Now the carbon chains are only held together with LDF. They need to be separated. There's some energy there, but not a lot. Step 2 is large, endothermic, especially with water. There's lots of hydrogen bonds in there. So separating water from water takes a lot of energy. And then step 3, again, since one's polar and the other one's nonpolar, these interactions are very, very small. So then we would have an endothermic solution. We would have to put energy into making that solution happen. My second example would be an ionic solution. So step 1 is going to be endothermic and most likely pretty large. And I want you to think about something here, because when you look at your solubility rules, and I know you're supposed to memorize like group 1 is all soluble, nitrates are all soluble. This is what this is all about here. Endothermic, the first step here, if that lattice is too strong, then water's not going to be able to pull this apart, and I'm not going to have an exothermic process overall. So step 1 is very, very important to ionic substances. If this lattice energy is too large, I'm not going to get past step 1. If I have a smaller lattice energy, with say something with group 1 with only a positive or +1 charge, then this is going to be endothermic, but not huge. So step 1 is all about separating the lattice. If it's ionic, step 2 is the same as it was before, hydrogen bonds with the water. And then 3 is going to be really exothermic because they're both polar. But since ionics and water we already know are going to get along, so step 3 is always going to be exothermic. Again, with ionic substances, it all comes back to step 1. Is the lattice energy too strong to be pulled apart in the very beginning? All right. There is one other piece to this, and it's called the enthalpy of hydration. And it's really just combining step 2, expanding the solvent, and the solvent solution interactions. In other words, if we take out the lattice energy part of step 1, if it's ionic, or if we take out the intermolecular forces of something that's non-polar and only focus on the expansion of the water and their interactions, then we're talking about heat of hydration. Okay, it's just about their interactions and the water itself. I have a third example here. Heat of the solution. So if I'm putting table salt in water, my first step, we're looking at the lattice energy right here. And if you look, this is a lattice energy reaction here. I am taking a solid and I'm taking it apart into its gaseous ionic components. And so the lattice energy for table salt is 786 kilojoules. Step 2 and 3, the separating of water and the interactions. So in other words, this is my heat of hydration right here. Steps 2 and 3 combined. And if you look, oops, sorry about that. If you look at the H right here, it says HYD. That's telling you that's the heat of hydration. So this is step 2 and 3, expanding the water, allowing them to interact, and I have an exothermic process of negative 783 there. Overall, by adding these together, I do have an endothermic solution, but it's really small. This is why when you put salt in water, it normally won't just dissolve on its own. Normally you have to stir it a little bit. But then once you get it going, it normally will go ahead and separate. In the book, it does give us this table that kind of sums up the 4 situations of a polar solute, nonpolar solute, and so on, and gives you kind of the outcome. It's probably a good idea just to take a look at this and make sure that you understand it. The last practice problem I have here is really just trying to decide what goes best with what. And this is something we've talked about in Unit 9, but keep in mind when we're trying to make a solution, like dissolves like. So we're trying to decide whether liquid hexane, which is a nonpolar solvent, or liquid methanol, which gives us this little OH polar alcohol here, and which one would be more appropriate given either of these 2 solutes. Well, grease we can see is a long carbon chain and definitely nonpolar. So we would want to use hexanes if we were trying to dissolve that. That would give us the best exothermic step 3, or interactions. Potassium iodide being an ionic and a weak ionic at that, I would use methanol to dissolve that. Okay, hopefully this has made some sense. As always, I encourage you to read this section in the book and let me know if you have any questions. Take care.